The next video is about Heron's formula, which can be used to find the area of a triangle when the three sides are known. It's a very symmetrical formula, as you would expect it to be. So notice here where S is you add up the side lengths and divide by 2, so A, B, and C are all symmetrically related there. And then here you have S minus A, S minus B, and S minus C. So these three factors are all entered symmetrically as well. So this formula is a highly symmetrical formula in the variables or side lengths A, B, C. Now it turns out it's kind of klutzy to use and easy to make mistakes, and in more advanced perspective, Heron's formula has what's called numerical instability. So actually, Heron's formula is rarely used to calculate the area of a triangle. So why do we include it? Well, it's included for some historical and cultural reasons. Let me come to back to that in just a minute. What do we do, really, if we do have to find the area in the side-side-side case? Okay, so assume we know the sides of a triangle, lengths A, B, and C. And then let's introduce the angle B opposite the side length B, right? I could also pick C or A, but I'm just going to use B here. So write down the law of cosines with B as the odd guy out. So B squared equals A squared plus C squared, like I'm doing some kind of Pythagorean triangle, right triangle thing. But now I have my correction term, minus 2AC cosine of B. So the point of this now is that because you know little a, little b, and little c, you can solve this for cosine of B. Okay, so let's suppose that we've solved this equation for cosine B, so we have some number here. Once I know cosine B, I can get the sine of B, because cosine squared plus sine squared equals 1, and I know cosine, because I know the law of cosines, and I knew A, B, and C. Next, what I do is I use the area formula, 1/2 base, right, base, and then the height of the triangle is drawn is C sine B. The height here is C sine B. So I use this variant of the area formula. Right, that's the formula over here, the third one, singling out the variable B. So that's how we would find the area in the side case using trigonometry. Law of cosines to get one of the angles, in this case cosine of B. Use the identity, cosine squared plus sine squared equals 1 to get the sine of B, and then use the area formula with sine of B to get the area of the triangle. Notice something about Heron's formula. It doesn't actually use any trigonometry. You just add up the side lengths and do a bunch of algebra, and then you get the area. And like I said earlier, it has some inefficiencies, but when you use trigonometry, like we did here, the calculation of the area becomes much more tractable, less prone to error. So back to the question brought up earlier, why do we include Heron's formula in a class here in the 21st century if the formula itself is not actually used in calculation and has issues like numerical instability? And it's kind of mind-blowing that Heron of Alexandria had discovered this formula maybe in 60 AD, way back, and it's thought that Archimedes also knew the formula maybe 200 years even earlier. What's interesting is that for the ancient Greeks, everything had to be understood in terms of geometry, so length, area, and volume. So all arithmetic to them was somehow tied up with geometry, length, area, and volume. But look at the stuff under the square root here. So we've got S, which is a length, S minus A is a length, S minus B is a length, and S minus C is a length. So this times this times this times this, well, that's going to be a length to the fourth power. So that's like four-dimensional geometry. And that really freaked the ancient Greeks out, that something could be, 4 dimensions could somehow be involved, which they just really freaked out about. But, when you take the square root of something that's 4-dimensional, you get something that's 2-dimensional, in other words, area. Right? So the square root of length to the fourth is going to be length squared, which has the right units for area. So anyway, the ancient Greeks had discovered this formula, and in spite of their insistence that everything in arithmetic and such had to be interpreted and understood geometrically, they bravely went on and said, okay, there's this 4-dimensional thing. I don't exactly know how they said it, but it's known that this was very disturbing to them.